Okay, classroom discussion for chapter 8. Here we go. First problem, calculate the angular velocity of planet Earth in its orbit around the sun and about its axis. Calculate the linear velocity in both cases. So, very interesting kind of rotation. I'm pretty sure you noticed that we have a planet Earth and it spins on its axis, and it also orbits around the sun. So both kinds of motion are rotational motion, so there is some kind of angular velocity involved in that rotation. So let's calculate both values. First of all, it's orbit around the sun. So with respect to the sun, how much time does it take for Earth to complete one revolution? Well, pretty sure you know it's 1 year. 1 year is the time for Earth to complete one revolution with respect to the sun. But unit-wise, don't forget that it's always seconds. You can't say years. And now for angular displacement, you need radians. So how many radians for one revolution? Well, think about something that completes one circle. That's circumference. For one circumference, one revolution, it's 360 degrees, which corresponds to 2 pi radians. Remember, it's 2 pi r for the arc length over the r, the radius. R cancels, and you have the angle in radians as 2 pi radians. So that's angular displacement, 2 pi. And for the time, it must be in seconds, and we're talking 1 year. So you start with 365 days, and 1 day is 24 hours, so days cancel. And each hour is 3,600 seconds because it's 60 minutes and 60 seconds. Hours cancel, and you're left with seconds. And you're going to get about 31.5 million seconds. So it's 2 pi over 35.5 million seconds, which gives you a very small value. It's 10 to the negative 7th. You take number 2, and you have to divide by 10 7 times. And remember, we discussed the free fall, and I said that the Earth travels very fast in its orbit. Well, that travel, it's not the rotation, it's the linear velocity, that is the tangential velocity. And there is a connection between linear velocity and angular velocity as r omega. We just discussed it in lectures, r times omega. This is how you calculate the linear velocity. And let's use the angular velocity that we just figured out, the omega, multiplied by r. R is the distance between the Earth and the sun. We calculate everything with respect to the sun now. So it's rotation. The radius is the distance between the Earth and the sun. And you can find that in kilometers in the textbook. Don't do kilometers. You have to convert to meters. Kilo means 1,000. So instead of 10 to the power of 8, you get 10 to the power 11 because it's times 10 times 10 times 10. So 3 more times you have to multiply by 10 to get to meters. From kilometers, this is the number that you're going to multiply by angular velocity to get the linear velocity. And once you do this multiplication, you get 30 kilometers per 1 second. This is approximately 67,000 miles per hour. This is how fast the Earth moves through space with respect to the sun. And don't forget that it's free falling, and everything is free falling in this world. So it's only because we move so fast in our orbit with respect to the sun that we keep on missing the sun. If we will slow down from the 67,000 miles per hour, we will fall into the sun. Thanks to conservation of angular momentum, this is not going to happen unless a super duper huge object hits the Earth and slows it down. Other than that kind of collision, we will keep on orbiting the sun over and over again for billions of years until the sun expands to a red giant and consumes us like you consume a Snickers bar or a bottle of water. So I just want to point out that we move pretty fast right now, this very second, through space because we are part of a solar system and we orbit the sun. Now it's Earth with respect to its axis. Part B says about its axis and how much time for one complete revolution around our own axis. I'm pretty sure you notice day and night. The change between day and night, it's 24 hours for one complete revolution. So once again, one complete revolution, 360 degrees, 2 pi radians. This is the angular displacement. And the moment of time must be in seconds. You can do hours. So 24 hours, convert that into seconds. Hours cancel, and it's 70-something thousand. Oh, it's actually 86,000 for 100 seconds. Divide those two values, you still get a very small value for angular velocity. It's 10 to the negative fifth. It's 7 divided by 10, 5 times. That's what you have as the result, radians per second. But once you multiply this ratio by the distance between the axis of rotation, which is the center of Earth, to the surface of the Earth where we all live on. So it's the radius of Earth that is the distance for consideration here. It is 6,400 kilometers. Don't do kilometers, convert to meters, multiply by 1,000. So instead of 10 to the power of 3, you get 10 to the power of 6. And once you multiply those values, you get 470 meters per second. Of course, it's not 30,000, but it's still approximately 1,000 miles per hour. So not only we go through space at 67,000 miles per hour because we orbit the sun, we also spin on our own axis, and that provides with an extra 1,000 miles per hour of rotation, the linear velocity for rotation along our own axis. Don't forget that X is actually tilted, and that's why we have seasons. It's not because the Earth is closer to the sun or further away from the sun. It's the tilt of the Earth that forces the northern hemisphere to lean towards the sun and get more sunlight. And 6 months later, it's the southern hemisphere that leans towards the sun and gets more sunlight, and it's summer for Australia then. It's, once again, not because the Earth is closer or further away. It's the tilt of the Earth's axis that produces seasons. Okay, we have a fan that is turned off, and there's an initial rate of rotation. We have 850 revolutions per minute. And it is given that it comes to a complete stop after completing 1,250 revolutions. First of all, you have to remember that there's no revolutions per minute. You can't operate with any of that. You have to convert to System International. And that would be what? Radians and seconds. So for angular acceleration, let's do the conversion. You have 850 revolutions per minute. Each revolution is 2 pi radians, and revolutions cancel, and you're left with radians. And then each minute is 60 seconds, and you see how minutes cancel, and you're left with seconds at the bottom. So radians on top, seconds at the bottom. That's exactly the System International values we have to work with for angular velocity. And if it's 1,250 revolutions, So consider the same conversion factor for radians versus revolutions. You get 7,850 radians. So you got your angular displacement. You got your angular velocity. It is time to calculate the acceleration, which you can use the two special set of equations because acceleration is constant. See how this is an analog of v equals v sub 0 plus at, and x equals x sub 0 plus v sub 0 t plus 1/2 at squared. So you replace all the linear parameters with angular parameters, and those are your kinematics equations for constant acceleration case. So it comes to a stop. That means your angular velocity is going to be 0 at some point, and initial value is given at 88.97. So this is the initial. We are not speeding up. Alpha cannot be positive because if it's positive, we're speeding up. We are slowing down to a stop, so it's a negative alpha times the time. And position-wise, you travel through this many revolutions. You can't do revolutions. You have to go with radians. So 7850 is your amount of radians for angular position, starting from 0, plus omega sub 0 is given at 88.97. T is the same T as you have for the previous equation. Time goes the same way for both equations. And alpha is what we're looking for. We're trying to solve for alpha. So this is your angular velocity equation, and this is angular position equation. So system of 2 by 2. You have time being unknown and alpha being unknown. This time you want to solve for alpha, but it doesn't really matter. You can solve for anything that's missing based on what's given. So from the first equation, I'm getting the substitution for time and substituted for the time, the expression instead of t. And you get 0.5 radians per second. This is your angular acceleration. Yeah, we put in angular acceleration with a negative sign because the fan is slowing down. Be careful. You have to show me negative sign for acceleration here and negative sign for angular acceleration there. You can't say it's positive because we're not speeding up, we are slowing down. Remember, for speeding up, acceleration and velocity should be the same sign. And for slowing down, acceleration and velocity must be opposite signs. So velocity is positive, therefore acceleration must be negative. Velocity is positive, acceleration must be negative if we are slowing down. So this is your angular acceleration. Next question was, how long did it take the fan to come to a complete stop? So how long means the time. For the time, we already have the expression. And then you figure out the angular acceleration, plug it in, and get the time. That's exactly what I'm doing here. Plug it in, get the time. 180 seconds, which is like what? 2 minutes, 3 minutes? Yeah, it makes sense. If the fan was rotating at such a huge rate, it takes some time before it comes to a stop. Yeah, time cannot be negative. Be careful if you say time is negative something, that just doesn't make any sense. But acceleration or angular acceleration or angular velocity can't be negative, so keep in mind those options. Okay, person exerts a horizontal force on the end of the door, 96 centimeters wide. Be careful, you cannot do centimeters, you have to convert to meters. What is the torque if the force is perpendicular to the door or at a 60 degrees angle to the face of the door? Definitely need a sketch. Let's take it out. Let's take a look. And here's the pivot point, and that's the door. And this is the force that you apply to the side of the door to start the rotation so that the door opens. And the torque is calculated as position vector, the force, and the sign between the two angles. So R and F, this is your angle of reference. If it's 90 degrees, it's just sine of 90, which is 1. The length of the door is given at 96 centimeters. 96 centimeters. The force is given at 42 newtons. So force is 42 newtons. And sine of 90 is 1. Boom, your torque is 40 Newton meters. Once again, do not convert Newton meters to joules. Joules are for work and energy, and Newton meters are reserved for the torque. Torque is not the same as energy, so this is how we distinguish between torques and work done and energy. Is it positive or negative? Well, if this is the force, then it will create rotation in the counterclockwise direction. So everything counterclockwise is positive. So torque is positive. Well, if the angle is 60 degrees, then all you have to change is just say sine, it was sine of 90 degrees, now it's sine 60 degrees. Sine of 60 is what? 1, 2, 3, so it's radical 3 over 2, 0.866 instead of 1. So the value is a little less, 35 Newton meters now. It was 40. Now it is 35. It makes sense because if the force is at an angle, it's going to be harder for you to open that door. And if the force would be parallel to the door, you will never open that door because there will be no tangential component to this force. So yeah, basically just a definition for the torque. And if you have problems with this definition, you can always do it. The force by itself times the moment arm. Moment arm would be the side of a right triangle. And for this one, you're going to need the magnitude. You're still going to multiply it by the sine of the angle. So either way, you will end up with this formula and this solution. Two blocks connected by a light string passing over a pulley. Blocks move with a certain acceleration along the frictionless inclines. Okay, at least no friction. That's a good thing. Free body diagrams, determine the forces of tension and find the net torque on the pulley. So here we are with a setup that we've seen before. This is your inclined plane number 1, inclined plane number 2, and we dealt with those blocks on the inclined plane with frictionless surface, not a big deal. The only change here is that we do have a pulley. And this pulley has certain parameters. You see the tension forces on one side of the pulley and the other side of the pulley, which are the reaction forces from tension in two different parts of the rope. So back in the days, we would say pulley is massless and you can't really think about any torque. Pulley does not rotate. Easy case. Now we say, hey, pulley is actually rotating, right? You have blocks moving and pulley is going to rotate. So we have to consider rotational motion for the pulley as well. That is the big difference between the previous inclined planes versus what we have now with rotation. So two types of motion. You have linear motion for the first block, linear motion for the second block, and rotational motion for the pulley. Here's the free body diagram for the block A right here. There is a string, a rope, or a cord, so there's going to be tension from the rope onto the block. So along the string, cord, or a rope, it's always like that. Normal force, normal is perpendicular to the surface. So if the surface is inclined, normal is perpendicular to that surface. And gravity is downward. Gravity is towards the center of the Earth. And it's given that acceleration is that way. So I'm just copying the direction for acceleration. And remember that the angle of incline here, theta sub A, is the same as the angle between the vertical axis and the force of gravity. So this is your free body diagram for block A. Block B, let's take a look at block B. What do we have? We have a rope, a cord, or a string. So it is along the cord. That's the tension force. This is your action, and that would be the reaction. So that's what force acting on the block. What else is acting on the block? We have normal reaction from the surface, and normal is perpendicular, so it is perpendicular to the surface. And then gravity downward, as usual, towards the center of the planet. And if the top block goes up, then the bottom, then the other block goes the other way. So my acceleration is in the opposite direction now. And the angle of incline is the same as angle of incline adjacent to gravity. So that's the free body diagram for the second block. And this is what we have for the pulley. We have action from block A, and this is the reaction from block A. We have action from block B, and this is the reaction for block B. So our pulley is under the influence of two forces, and this force creates what? Counterclockwise. F sub TA creates positive torque, and F sub TB causes clockwise rotation, so it's negative torque. So the net torque would be, one take away the other. Be careful with the signs. And yes, there is gravity on the pulley as well, but if this is the axis of rotation, then gravity has a line of action that crosses through the axis of rotation, zero moment arm, zero torque for gravity. So the boring inclined plane from the previous analysis that we did in the previous 7 chapters, F equals ma, normal is perpendicular, so it's zero, tension is by itself, your gravity has a negative and a sine component, the gravity onto x, that's the component I'm talking about. So it's opposite to theta. If this is theta, then this is theta, and this component is opposite to theta, and it's pointing the opposite direction to x, so it's a negative mg sine theta. And what's the acceleration? Acceleration has the same direction as the positive x-axis, so it's plus ma right there. Onto y-axis, it's all normal force, and now gravity is also opposite, and it's opposite direction, but adjacent to the theta, and that's why it's a cosine function, but it's a negative because it's opposite to the positive y-axis. So it's cosine and it's negative. Everything else is perpendicular onto y-axis, so that's just zero. Acceleration is zero. Acceleration is perpendicular onto y-axis. Y-axis, acceleration perpendicular, so it is zero. So calculating the tension from what's given, 50 newtons, yeah, makes sense for for a small setup. For block B, same equations. Positive for sine, negative with cosine. The free body diagram tells it all. Go ahead, check your understanding of components. You will get 76 newtons for the tension, which is consistent with what you expect. You need this tension force being greater than tension in for A because the overall rotation is clockwise. So F sub TB wins over F sub TA. The whole system, block B goes downward and block A goes upward. So 76 wins over 50. That's why you have this kind of motion. And the last equation to figure out what's going on with the pulley is the second Newton's law, the rotational version. You have the net external torque. What kind of a torque do we have? It's the force times the moment arm. Moment arm is the radius of the pulley because it's the shortest distance between the axis of rotation and the line of action for both forces. That's the line of action. That's the axis of rotation, and the radius is the shortest distance. That's the line of action. That's the axis of rotation. That's the shortest distance. So it is the force times the radius for both cases. But be careful, one of the forces creates a negative torque because there is a clockwise direction for rotation. Overall torque is negative. Makes sense because, like I said, the overall rotation is clockwise. So net torque is a negative 3.9 Newton meters. And now the dynamics. Dynamics means the net external torque is your rotational inertia times the angular acceleration. We have no idea on angular acceleration, but we know that there is connection between linear parameters and angular parameters. Remember, the A is R alpha. So now I want to replace alpha with what's given. Remember, A is given. A is 1 meters per second, and R, the radius for the pulley, is also given. So I don't need alpha. I can just replace it with what's given in terms of linear parameters. This is a beautiful way out for when you need angular parameters, but you have only linear parameters given. And you can do it vice versa. Let's say angular parameters are given, go backwards, solve for linear parameters, use it for your translational motion. So torque is given. I mean, we figured out the torque. A is given, R is given, solve for the rotational inertia, or you say moment of inertia. You got 0.59 kilograms times meters squared. Why is it kilograms times meters squared? Remember the general formula, mr squared. M is the mass, boom, and r squared is the distance squared, so meters go squared. This is your net result for rotational inertia. Okay, one last thing for kinetic energy. Remember 1/2 mv squared. That was translational motion. Instead of mass, you go with rotational inertia, so I. And instead of v squared, you go omega squared. For a bowling ball, what do we know? It is both rotation and translation. So total kinetic energy is the sum total between the translational and rotational parts. So 1/2 mv squared and 1/2 I omega squared, that's what you have to solve for. Okay. We have a bowling ball. That's not a particle. Can you think about a certain geometry that a bowling ball represents? Well, if you ever played bowling, you've seen that those are really close to be spheres. So it is the rotational inertia of a sphere that you have to keep in mind. And you have to look up the coefficient for the rotational inertia for a sphere in that special magic table that we discussed in lectures. Once again, you don't have to remember all of those coefficients. I will give them to you for the test and the quiz. But for now, just take a look at the table and copy the 2/5 mr squared. That's the rotational inertia. And then do not forget that you can also connect the linear and angular velocities through this little expression and replace the do we have all things given? 2/5. Yeah, you have to replace the omega squared with v over r squared. See how it's I omega squared, but you don't have the omega. Omega is not given. But you might say omega is just v over r because v is r omega. So instead of omega squared, you say I want v squared over r squared. That's exactly what I'm doing right here. So instead of omega squared, it is v squared over r squared. So it's 1/2 mv squared from linear motion as usual as before. And now your rotational kinetic energy is 1/2, 1/2, 1/2. And your rotational inertia is 2/5 mr squared. We borrowed that from the special table for coefficients for rotational inertia of different geometrical objects. So 1/2 mv squared plus 1/2 2/5 mr squared, that's 2/10. And r squared cancels out. That's very convenient. So you have 1/2 plus 2/10 of the same thing, of the mv squared. So it's mv squared and 1/2 plus 2/10. That gives you 7/10 mv squared, which you can just leave as the final answer, but mass is given. Mass is 7.25. V squared is also, V is given, so square the V and get the 48.8 joules. Remember, energy is in joules, torques are in Newton meters, even though dimension-wise it is the same result, but Newton meters are reserved for torques, and for energy, you have to show joules, and work done is also joules. Okay, that's it for your basic rotational motion. I'm gonna stop the recording.